Assalamu alaikum everybody for lecture number 7 about reflector antennas. So what are reflector antennas and how can we do analysis for them? So this is the first step in order to design an antenna, a specific type of antenna, is to be able to analyze it. So this is the first step, is to define what is reflector antenna and how would we analyze it as a first step towards designing. In our course, we'll not focus on the design, just like my goal is to get you familiar with how the reflector antenna works and what are the possible ways to analyze them. So as shown here on the slide, we have many types of reflector antennas. We can have like this reflector antenna, just like a straight conducting plane. You have a feed that you send the signal and it is reflected. Another reflector antenna like this one, which is a corner reflector antenna, you have the feed. Depending on the position of the feed, you can depending on the position of the feed as well as the angle of the reflector, you can control its radiation pattern. This is a very common or very popular reflector antenna, paraboloid, where we have like a feeding point and it's illuminating the metallic surface of the reflector. Then it is reflecting the signal like in parallel format. There is another type which is a double reflector. You have the feeder from this point, it goes into a reflector. The reflector sort of like diffract or the signal to illuminate this parabola, and then the parabola would have like the signal goes out of the antenna. So the very early type of reflector antenna, where the corner reflector, like this one here. So this is like a side view. Like we can have like different angles. We can have different position for the feeder, and when it is implemented, it would be something like that. And the design parameter for this, like what are the length of the antenna, what is the angle, where is the position of the feeder, how long, what is the height of the reflector, so on and so forth. And this like plane sheets or like this solid corners can be also replaced by a grid depending on the frequency. So if we have like the spacing less than lambda by 10, this would act as like a good approximation for a solid plane reflector. But of course, this is much lighter and much less expensive. So there is multiple formats. What I'm saying is there is multiple formats of those corner reflector antennas. And how would we analyze this? Like image theory is a very good method to analyze for the corner reflector antenna. There is some acceptable approximation regarding like the length of the two sides of the corner, regarding the height, the total height of the reflector corner antenna, regarding with respect to the feeder. But it is a very good and acceptable approximation to do this. So the use of image theory is like this. I'm going to return to this slide again. So if we have like this corner reflector antenna that's 90 degrees, and we have the feeder here, and this is like the top view of the reflector antenna. This is the source or the feeder. How would we solve this problem? Like using the image theory. We like discussed this before in electrostatic. And the idea here is very similar. We have like a source here, we have a grounded metallic plane, we assume it's infinite. So the idea is to fulfill the boundary condition on the corner. So we have an opposite orientation for this feeder, so that we fulfill the boundary condition on this arm. We have like another image to fulfill the boundary condition in this arm. But after we do this, because of like the two elements, like they like sort of like disturb one another, and we need to add a fourth feeder or like a third image with the same polarization as the feeder, so that the boundary condition is fulfilled on both sides. So for 90-degree, we need to use like 3 images, or we have like 4 sources. If we have a different angle like 60-degree reflector, you will discover like from the image theory that you need to have 6 elements or 5 images. So this one, the first is it's opposite. Then we need to correct for this. We add one here. We need to correct for this. Then we close the loop with this. If we have like 45-degree, you will find that you need 8. If you have 30-degree, you will find that you need 12. So in general, if the angle of the reflector is 180 divided by an integer, so we will have like a number of images plus source equals this. So if the angle is 90, so alpha is 90, which is 80 over 2, we'll have 360 over 90, we need 4. If it's 60, we need 6. If it's 45, we need 8. If it's 30, we need 12, so on and so forth. As far as alpha is an integer part of like, or alpha equal 180 over whatever integer. If we have a different angle, for example, if we have an angle equal 80 or 75 or like 100 or whatever, so the problem would be solved by an infinite series of sources. So there is some solutions for this if we our like corner reflector angle is different than those like very famous ones. So this is the idea of like how we use the image theory to solve for this problem. So here, let us see how we solve this. It's very similar to the array problem. In this case, we have like a 2D array because they are arranged in XY plane. So it's a 2D array. For like any array, we have pattern of the feed element or the element factor. Then we have the array factor. Again, we use the same approximations that we did before. Any element is e to the minus jk r1 divided by r1, where r1 is the angle from the center of the source to the observation point, and we have the very like famous approximations that we did for the amplitude terms. We approximate all the elements to be the same value r, which is from origin to the observation point. The origin in this case, for example, would be like this point. And for like phase, we have like r1 equal r minus s, which is the distance from the origin to the feed point or to the source, that is the s4, cosine phi 1, where phi 1 is the angle between r prime from origin to source 1, from origin to source 2, from origin to source 3. So this is ar prime dot ar, where ar is from origin to the observation point. Like we did this like many times for wire antennas, we did this for aperture antenna, we did this for antenna arrays. So it's the same like approximation. And in this case, we can just like rewrite or write the expression for cosine phi 1 for the first element. The first element is along the x-axis, so the AR prime is AX, AR is AR from origin to a general observation point. For element 2, it is AY. For element 3, it's minus AX. For element 4, it is minus AY. So we have those 4 expressions for the cosine. Of course, the cosine can be found by the dot product of 2 unit vectors in the directions of those vectors. So now we can just like do this, and AR can be expressed in Cartesian in this format, so that the total electric field from this reflector antenna would be the element factor multiplied by the array factor. The array factor is this 4 elements. We can find from the expression here 1 and 3 can be like combined together to have a cosine, as we're going to see in the next slide. 2 and 4 also can be combined together to form another cosine. So the total radiation field from this reflector would be like the common factor. Then like this is element 1, element 3, they can be combined together to have cosine 2 twice cosine this expression. This element 2 and element 3 with the negative sign can be combined together to have another cosine. So the array factor, which is E divided by E naught, the element factor, does have this expression. So this is the array factor, and you can see that it's having or affected by theta and phi, because it's a 2D. It can scan in, or here we are not scanning, but it has pattern in both planes, the azimuthal plane and the elevation plane. So here we can, like, for multiple different values, S, which is the space between the source and the origin, is 0.1 lambda, would have this pattern. It's a nice pattern. And then with different values, we'll start to see like multiple loops. And one important thing here, because the antenna is like 90-degree antenna, there is no radiation outside. We are focused our pattern into this 90-degree of the reflector. So it is like a sort of like an idea for focusing the signal into a specific direction. And one thing regarding the radiation patterns that I saw in the homeworks, that for example, if we are scanning for theta, you must pay attention that theta change from 0 to 180. There is no reason to like go from 0 to 30 to 360. And also, like, the radiation pattern is a single value. You can see like loop inside a loop, because if you have, like, for example, like if you have, let me draw this. So for example, like we can't draw like a radiation pattern like this. There is nothing like this, because in this angle, for example, if this is whatever angle, and this is, so okay, so in this direction, what is the value of the radiation pattern? Is this value or that one? So it can't be this way. It must be like a single value function. If we have a loop, it would be something like that. It can't be anything inside it. So this is also like one of the problems that I saw in the homework. Okay, so let me draw this. So pay attention to which angles that you are scanning, depending on the kind of problems that you are solving. So moving from the corner antenna to more advanced and now more conventional antenna, which is the parabolic reflectors. The parabolic reflector started by this idea here, like parabolic cylinder. So we have similar to the corner, but instead of just having, let me bring this back. Okay, instead of just having a corner, now we have like a curved surface that is doing the reflection. And the more advanced and more conventional reflector that is very common nowadays, for example, for dish receiver, is the paraboloid, where we have a paraboloid part of a surface and a feeder if we are like submitting, or a collector if we are receiving. So the idea of this paraboloid is depending or like coming from geometrical optics, where it has been shown that in the receiving mode, parallel rays incident upon a reflector, like a dish receiver or satellite receiver, the signal is coming from very far, so it is like falling on the surface of the reflector as a parallel rays. Upon this reflector, the geometry is a parabola. The radiation will be converged or focused to the spot that is known as the focal point. So this is the idea of this satellite receiver. You have a surface, and this surface is pointing towards the satellite. The satellite is very far, so the signal or electromagnetic waves coming from satellite is like coming in parallel. So it will be collected similar to like an optical like reflector. It will be collected and focused on the focal point, and so like we are collecting a large amount of data so that we can get like a good signal. So this is when receiving, and from reciprocity we can think about the transmission the same way. If this focal point is emitting a signal that is illuminating the reflector, this would result in a transmitted wave that is going parallel out of this reflector, which is like a large area, and it is very useful in satellite communication, for example, or focal, like point-to-point communication. So, for example, like this is like a very big reflector antenna that is 10 meters, that is dual reflector. We have the signal going from here, like it hits reflector 1, it illuminates reflector 2, and the illumination from reflector 2 is going like this is a transmitted signal. And as you can think, this is large, so it's large electric dimensions. The like beam width is very thin, so that it can travel for very long distance, and this is what we need for satellite communication. Okay, what is the proper geometry of the parabola? So if this is the focal point, we'll assume the focal point is the origin, and we'll assume this is Z. Then we have Y, and we have X, which is perpendicular out of X is perpendicular out of the screen here, and this is what we have. So the idea here from geometric optics, at any point we choose the surface such that the signal goes from here, will go to the surface, then reflected. The reflection here is following the geometric optics, so we have the normal to the surface. So depending on the incident angle alpha, the reflected angle beta will be equal the same value from Snell's law. And the idea is that we choose the surface S such that at any point the reflected signal is parallel to the z-axis. So we have like a parallel rays going out of this reflector, and this way we can have like a uniform illumination over a very large area, so that we can have a smaller and smaller beam width. So this is the geometry here. Let us like go for like the mathematical description for this geometry. So the idea here is to have from the source to the point, any point on the surface. So from the source to any point on the surface up to like this point Q, we have this length. We need to be in phase with this length and B here is general, and if we achieve that, all the points on this surface will be in phase. So all of them will be in phase, and this means like we have like very good beam width, smaller beam width. If we have like a mismatch in the phase, we would have a problem because you will have destructive interference and wouldn't achieve the intended like small beam width. So this is 0, B, B, Q. So this length, if it's equal this twice this length, it means that the signal that goes and reflected from this path travels the same distance as the signal from this point, as the signal from this point, as the signal from this point. So at this point, all the like smaller point or secondary sources or wavefront would have an phase wavefront. So how we choose the surface S to fulfill this requirement? So the idea here, we call OB equal R prime, BQ equal R prime cosine theta prime. Can here again, this is theta prime, this is R prime. You can see this is the distance, and then for this right angle would have this length equal R double prime cosine theta. Okay, cosine theta prime, this is theta prime, and this is the length R prime cosine theta prime. So this is the two elements, and we want this to equal 2f. F is the distance from focal point to the antenna, from focal point or source to the center of the paraboloid. So just to go with the math, we can find the condition for that. The condition for that is R prime equal F divided by cosine square theta prime over 2. Just to continue with the math. So the condition for parabola, like if we go for Cartesian coordinate system, any point here would be x prime square plus y prime square plus z prime square under the square root. This is R prime, and this part would be z prime. So this is R, this is R prime cosine theta, or this is OB, and this is BQ. We need this to equal 2f. Just do the math, would have like a formula for parabola, and this is the surface equation of this paraboloid surface. So this is the expression for R, and this is the equation that is describing S in spherical coordinate system. So this is the equation of surface in spherical coordinate system. Now we would like to find the normal to any point. So the normal to this surface equals the gradient of S. So this is the meaning of the gradient operator. So the gradient of this expression in a spherical coordinate system will give us the normal, the vector normal to the surface. So we just do the gradient on Cartesian for this function. We'll have this expression, this is n. We need to find the unit vector. We just divide by the amplitude, and we'd have this expression here. Okay, so it has like R component and theta component, and the normal for this operation is just we divide by cosine theta as a common factor. The remaining would be cosine plus sine, which is always a unity. So we have this is the unit vector normal to any point on the surface that is defined by angle theta prime. So this is theta prime at any point on the surface. This is the expression for n. So from we need now to calculate alpha, we need to calculate beta. So cosine alpha equal an dot product with ar prime. Just do the math, we'll find this equal cosine theta prime over 2. So this angle is theta, this angle is theta prime, this angle is theta prime. We just prove from the math that cosine alpha equal cosine theta prime over 2. Same thing for cosine beta, it is equal cosine theta prime over 2. So the Snell's law is applicable. The geometry or the choice of the surface S this way fulfill the geometrical optics of and Snell's law, which is incident angle and reflecting angle are equal to each other. So now, after understanding the geometry of like the very common paraboloid reflector, now what are the different ways to analyze reflector antennas of this type? So we actually have two methods. Method number one is induced current density. Method number two, aperture distribution. So for method number one, we need to find the surface current on the paraboloid, and then we can use the auxiliary function A to find the value. We integrate over the surface. Once we have A, we can just find H, and we can find E. So the idea here is to find the surface current on the paraboloid, use the surface current as our source. We find the auxiliary function A. Once we have A, we can find H and find E. So we have the full radiation. How can we get the surface current S? S equal N cross H. And now we have like two sources. We have for H, we have incident current, we have reflected current. So N is the normal, we get the expression for N. So we just add H incident and H reflected, because if you just see the boundary condition for a perfect conductor, this is approximately, you will find H incident and H reflected equal to each other. So the surface current would be 2 the normal to the surface cross product H incident, which is H incident and HR are the same in this case. So this way, if we know the feeder or the eliminator, we can find the electric field incident, or sorry, the magnetic field incident on the reflector. It will equal to the reflected field at the reflector antenna. So we can get the total current. We have surface current now. We apply the integration to find the total auxiliary function A. From A, we can find H and E. So this approximation is called like physical optics. And this is valid if the radius of the curvature of the reflector object and the illuminating wave is large compared to the wavelength. So this is good for large reflectors, which is very common to have like a large reflector with respect to the wavelength. So this is the first method, which is induced current density. So for TEM wave, we know that H incident equals the direction of propagation cross E over eta. H equal reflected wave cross E reflected over eta. So this is just a proof because E reflected and E incident are opposite to each other, but also SI and SR are not the same, they are in different direction. So we can prove that, or we can use whatever one of them to find Js from incident or reflected electric field at the surface of the reflector. So this is the idea. We have illuminator. The illuminator will produce some electric field on the surface. We can use this to find J. Once we find J, we can find A by integrating over the whole surface. Once we have A, we can find E and H. So the other method or second method is aperture distribution method. So the advantage of the aperture distribution method is the integration over the aperture plane is much easier, and it's very similar to what we learned from the aperture antenna. The integration of the surface of the reflector required for the current distribution method is complex, because you are taking like the incident field, and you have the from point to point you have a different orientation for the normal. So in general, the current distribution method, maybe it's accurate, but it is like more difficult to implement. The aperture distribution method is easier. So this is what this slide is saying. So how would we do the aperture distribution method? We have the following steps. So the field reflected by the surface is first found over a plane which is normal to the axis of the reflector, similar to this. So we choose a plane, we find the field on this plane. And in this case, we assume that the field exists just on this part of the plane. We neglect anything that's going, it's called spillover. We neglect any spillover outside this opening of the reflector. So this is like a very good, it's an acceptable approximation. So how would we do this? General like geometrical optics, similar to this reflection like concept that we use to find the geometry of the surface of the reflector. And we most of the time find this to go through the focal point. So the focal point is defining the plane where we calculate our field, and this is called the aperture plane. Once we have the field on this aperture, we can use equivalent sources to form a plane. Usually it's assumed, as I said, the equivalent sources are zero outside the projected area of the reflector. Then we use the same methods for aperture techniques to find the radiation from this reflector. So this is the case. Depending on the feeding point, we calculate the field that is bouncing from the reflector back to a plane, the aperture plane. We neglect any spillover outside the projection area of the opening of the reflector, and then we will have certain illumination on the surface. We use this data as like aperture antenna and equivalent theorem, and we solve for the problem. So the remaining for this lecture is for you. I don't want to go deeper into reflector antennas. I just like showed the concept for corner reflector antenna, for the very common parabolic antenna, the different ways to solve like or analyze reflector antennas. And I prefer to stop here, and in the future, if you are to deal with reflector antenna problems, you have enough knowledge to know where to start and what to do. And this would be like the end of this lecture. Thank you, everybody.